Hey guys, it's UCM Universal Circular Motion results from this morning's uh, class, and we got this one, which is the three graphs, which is very important to, I guess, to centrifugal motion. And right here, as we can see, is that this is our graph. The graphs for all of them were relationships of net force and speed, net force and radius, and net force to mass. So they're all directly proportional in many ways. Let's start with the speed. For the net force, for every two net force, for example, two net force, the speed doubles it. So it doubles it because it's speeding up over time. It's accelerating. It's constantly accelerating, and we can show it in the graphs, or we can show it even in the UCM FET. Same, and if we actually want to put this into uh, an, a linear graph, we would see that net force is proportional to speed squared right here, because we're squaring the speed. That means if net force was 2, it would be 4. 2 squared equals 4. If net force was 3, it would be 3 squared equal to 9. So in order for us to make this into a linear equation, we can just make v squared, because v is representing speed. If we put v with the arrow on top, that will be velocity. So we did an acceleration. Here we have a radius. The radius, it's the relationship between net force and net force and radius. As we can see, is that the net force is higher if the radius is smaller. So basically, if, for example, hold on one second. So for example, if this is, let's see, like the center, and this small thing is right here, is the radius, then this will go by fast like that. Whee! So it's going by really, really fast. Right here. So if we go back here, as it goes on, the net force lowers down as the radius gets higher, and the radius gets higher and higher. And we can put that to where here, right there, and it's going slower because there's more tension. So if there's no more tension, there's actually some some tension against it, going against the speed, compared to the first one. Compared to the first one, where it's right here, it goes really, really fast because there's less tension. And it's net force is directly proportional to 1 over r. We can put this into 1 over r, because we can just divide half. We just half this. I'm sorry, yeah, half that. If here we're doubling it going high, then here we're making it half. So proportional, we can make 1 over r. So for this to become a linear, so net force is linear to 1 over r, or 1 over radius. For net force, the relationship between net force and mass is they're just directly proportional. If we put like 1 kilogram, that will be one net force. So that's how we know there's a net force, because if 1 kilogram is a 1 net force, and they're directly proportional. If we actually want to put all of these equations together, like 1 over r, v squared, mass, we can go over to here where it's net force is equal m times v squared over r. And what we actually can figure out is what's really funny is that it's actually directly related to Newton's second law, which is the equation is net force is equal to m times a, where we see here v squared over r is equal to acceleration. And in this case, this equation is only used for centrifugal, I guess, in the centrifugal motion, where m times v squared is over r, because you can see here it's towards center, so we want to find the acceleration that goes faster towards the center over time, the constant acceleration. So v squared over r is basically, that's how long the acceleration of the vector, that's how long we want it's towards the center acceleration. And this one is this fish symbol is a proportional symbol. And yeah, that's it.